Okay, now we're going to start learning about trigonometry. And trigonometry is the study of angles in different forms. Sometimes angle in a triangle, sometimes angle in a circle, sometimes angle in a pie-shaped piece, which we call a sector. Lots and lots of angles. So, we need to understand what we mean by an angle. And what we mean is, you start with a ray, which is one of these half lines, okay, and it is called the initial side, and imagine turning it until we reach this side that we call the terminal side. Okay. Then that angle theta, which is a Greek letter, we usually use Greek letters for angles, is the measure of how much we turn to get from the initial side to the terminal side. This point at the end, around which the line was turned, is called the vertex. Now, there's a little bit of a quirk. Okay. In mathematics, all angles move counterclockwise when they're positive. Okay. It's actually the way things naturally work out. So if you want an angle that moves clockwise, as you may be more used to, you have to do it as a negative angle. So, negative angles are perfectly allowed. They just mean that you're moving clockwise instead of counterclockwise. Now, we have two different ways of measuring angles. And the first way is the one you're probably very familiar with, and the second you may not have heard before, but it's much more useful and understandable. So, when we're talking about angles, we're often going to be looking at a circle. Okay. This is the radius, also the initial side. We turn through some angle to another side, which happens to have the same length, also r. Okay. Now, in degrees, which is the way you may have been familiar with measuring angles, there is no nice definition of where a degree came from. Okay? It's actually a holdover from the Babylonians because they liked a sexagesimal number system. It means base 60. So they were actually trying to get to how many days in a year by how many degrees in a circle. So degree, it is simply 1/360th of a circle, which is a really bad definition because it doesn't really come from anywhere. But it is what we are used to. And there, of course, 360 degrees in a circle. Now, what we would really like is we'd like something that makes a little bit more sense. So, looking at this little slice of a circle, I'd really like the measure of the angle to be related to how long the edge is that it turned through. Okay, this is called the arc length, and it's always denoted with S. Okay, so we would like the measure of that angle to somehow be related to the arc length it cuts out, which is S. Okay. But we run into a little bit of a problem. Okay. If you were to look at a clock sitting in a classroom, for instance, it's about a foot across maybe, and when its minute hand moves from 12 o'clock to 3 o'clock, it goes through a fourth of the circle. Okay. But the tip of the minute hand, the arc length traced out, is actually a relatively small distance because it's a fairly small clock. Now imagine that you got to go to Big Ben in London with a huge clock that's tons of feet across. Now, the problem with this is that when the minute hand moves from the 12 o'clock to the 3 o'clock on Big Ben, it's still only moving a fourth of the circle. The angle hasn't changed, but the tip of that minute hand is traveling feet instead of just the inches from the classroom clock. So we want a way of measuring angles based on their arc length, but that doesn't matter how big the clock is. Okay? And the way we do this is with a relative arc length. Okay? So the radian measure of an angle is defined to be the arc length cut out by that angle divided by the radius to counteract needing to know how big the circle is. The interesting thing about this is if you look at units, S and R, arc length and radius, are both lengths. So they both might be measured, say, with inches. And then inches divided by inches would cancel out and I'd be left with no units. So one of the actually most useful things about radian measures is that they are what we call unitless. There are no units attached to a radian measure, unlike a degree measure that has that little degree symbol attached. this is actually going to be very useful for us. We do, however, often write rad or radians after, just to let us know that we're talking about a radian measure. Now, one thing before we do a couple examples is, just like I knew there were 360 degrees in a circle, I now need to know how many radians there are in a circle, okay? And that's not something I'm very familiar with. So, in a circle, let's compute how many radians there are. The angle cut out as we go all the way around the circle will provide the circumference as its arc length, okay? So S will be 2 pi r divided by r. The r's cancel. So in a circle, there are 2 pi radians. So you'll notice that most radian measures are going to carry that pi throughout. Okay. All right, now we're going to do an example of converting back and forth between degrees and radians. Let's start with 235 degrees. If I wanted to convert this to radians, I'm going to use a conversion factor. And a conversion factor is multiplying by a fraction where the top and the bottom may look different, but they actually represent identical things. So, what I'm going to use is the fact that 360 degrees equals 2 pi radians. I'm actually going to divide that through by 2 and use that 180 degrees is pi radians. So, I'm going to multiply by a fraction where the top is pi and the bottom is 180 degrees, because these are actually equal though they look different. Now, how did I choose which one on top and bottom? Well, I want to end up with radians, so that one on top, and I want to cancel the degrees, so that one on bottom. Because now the degree symbol cancels, I'm left with 235 pi over 180, which simplifies to 47 pi over 36. And that's the radian measure of 235 degrees. Now let's do one going the other way around. 3 pi over 7 radians. Once again, I'm going to multiply by a conversion factor, only this time I want to end up with degrees, so it goes on top. And I want to cancel radians, so pi goes on bottom. The pi's cancel. Now, unlike converting into radians, where you always want a nice pretty fraction, converting into degrees, we often want a decimal representation. So this is 77.1428571 degrees. And it goes on a little bit, but we'll stop just at that. Okay? And so now we have a way of converting between our two ways of measuring angles, degrees and radians.